It probably doesn't come as a shock to you that some of the biggest software services and apps we use every day aren't running as one monolithic service. Behind the scenes, there are usually tens, if not hundreds, of microservices that power the software we interact with. Think about it. When you request a ride on Uber, for example, one service might handle your authentication. A different service might calculate the fare and find nearby drivers. A third service might manage real-time location tracking, while another completely different service takes care of processing your payment. Some of these services sit directly in the path of a live user request, so they need to respond quickly to avoid slowing down the user's experience. Others work behind the scenes, analyzing traffic patterns and optimizing driving routes, which can take minutes or hours to complete. But here's the thing. Regardless of whether these services need to respond in milliseconds or can take their time processing in the background, they all share one critical requirement. They don't work in isolation. They constantly exchange data with each other to deliver the seamless experience you expect. As you'd imagine, there are many ways these services can communicate, each utilizing different protocols depending on the specific use case. Some services need that data right now, this instant, or the user experience falls apart. Others can wait and receive updates eventually when it's convenient. But the communication style also depends on other factors. How much data needs to be transferred? How reliable does the delivery need to be? What happens if a service is temporarily down? Should the communication be one way, or does the sender need confirmation that the message was received? Several communication mechanisms have been developed to account for all of these constraints. In today's video, we're going to explore the most popular communication patterns used in real-world distributed systems, from synchronous API calls to asynchronous message queues and everything in between. Let's get into it. Let's start with the most familiar and the foundational form of inter-service communication: APIs. APIs have been around since the 1970s, originally existing as software libraries that helped programs communicate with operating system or handle low-level tasks. Back then, everything ran locally on one single machine. They then evolved in the late 1990s when the internet really became a thing. Suddenly, services needed to talk to each other across the network, not just on the same computer. Enter SOAP, or Simple Object Access Protocol. Microsoft and other industry bodies introduced SOAP as one of the first web-based APIs. SOAP brought structure and formality to how services communicated over the web using XML messaging. While it was groundbreaking for its time, SOAP quickly revealed its limitations. It was heavy, complex, and rigid. Developers found themselves wrestling with verbose XML schemas and complicated protocol requirements just to send simple requests. Then REST arrived and completely changed the game. REST is short for Representational State Transfer. It was introduced by Roy Fielding in his doctoral dissertation and offered a radically different approach. Instead of complex protocols, REST leveraged existing HTTP infrastructure that already powered the web. Developers could now design APIs using familiar HTTP methods like GET to retrieve data, POST to create new resources, PUT to update existing ones, and DELETE to remove them. REST adoption was swift and decisive because it was lightweight, intuitive, and blazing fast compared to SOAP. The secret sauce was JSON. While SOAP relied on bulky XML, REST embraced JSON's compact human-readable format that browsers and servers could parse easily. In practice, when one service needs to communicate with another, it sends an HTTP request to a specific URL endpoint. This endpoint is a digital address of where the service is located on the network. The request might carry data in its body, called the payload, usually formatted in JSON. It might also include parameters directly in the URL to specify what exactly is needed. The receiving service processes this request, performs whatever operations are needed, and sends back an HTTP response. This response includes the status code telling you whether everything worked smoothly along with the actual data you requested. An example of a GET request fetching products in a category from a product service might look something like this, and the response might look something like this. In a complex flow, a shopping cart checkout process might involve a POST request to the payment service to authorize the charges, a GET request to the user service to fetch the customer's delivery address, and finally, a POST request to the order service to officially record the purchase in the system. Each step waits for the previous one to complete successfully. If the payment fails, the process stops there. If the address can't be retrieved, no order gets created. This sequential dependent flow is where REST APIs truly shine. It excels in scenarios demanding immediate responses. When you're processing a payment, you can't tell your customer, wait, we'll get back to you later as to whether your card worked or not. You need that confirmation right now. APIs are also perfect when your calling service simply cannot proceed without a response. If the next action depends on the results of this one, like confirming a user's password before granting access, then APIs are the right tools. For standard CRUD operations, create, read, update, and delete, RESTful APIs feel natural and intuitive. They map out beautifully to HTTP methods and provide a clear, predictable interface for managing resources. But REST APIs aren't a universal solution to every inter-service communication. They create challenges in certain scenarios that actually make your system more fragile and complex. The biggest issue is tight coupling. When one service becomes heavily dependent on another's availability, you're essentially tying their fates together. If your payment service goes down, your entire checkout process grinds to a halt. If your user service becomes slow, every part of your application that needs user data starts to crawl. This synchronous nature becomes particularly problematic during high traffic periods. Picture Black Friday when thousands of customers are simultaneously trying to apply discount codes. If your promotion service can't keep up with the flood of requests, those API calls start failing or timing out, creating a cascade of frustrated customers and a broken checkout process. REST also struggles with event-driven scenarios where one action should trigger multiple independent responses. Let's say a customer completes an order. That single event might need to notify your loyalty program to award points, trigger your shipping service to prepare the package, prompt your email service to send a confirmation, and update your analytics dashboard. Using REST for this scenario might mean your checkout service might need to make 4 separate synchronous calls and wait for each one to succeed. If your email service is down or having a slow day, your entire order completion process gets delayed even though the transaction is already done. Another massive problem with REST APIs is endpoint proliferation. As software systems scaled, REST endpoints began multiplying rapidly. Each endpoint was tailored to a specific need, and every new feature seemed to demand its own specialized endpoint. One for fetching user profiles, another for retrieving orders, one for product review, another for recommendation, and this list kept growing. Before long, developers found themselves managing dozens, if not hundreds of endpoints, each serving a narrow specific purpose. This made it nearly impossible to retrieve exactly what you wanted without orchestrating multiple API calls. Let's say you're building a personalized dashboard for customers in your e-commerce store. To render just one screen, your application might need to make multiple sequential calls. First, you'd call the user endpoint to fetch their profile information. Then you'd hit the orders endpoint to get their recent purchases. Finally, for each order, you'd need to call the product endpoints to retrieve details about what was purchased. That's 3 API calls for one dashboard, and there could be many more. But what if all you really needed was just the user's name and the name of the last 2 products they ordered? Sounds simple, right? But look at what the user endpoint might be returning. The response comes back loaded with information: their full name, email, phone number, complete address details, date of birth, and much more. You're pulling in a massive JSON object just to extract 2 fields, the first name and last name. This is a textbook case of overfetching, where you're forced to download way more data than you actually need. Not only does this waste bandwidth, it also slows down your application and creates unnecessary load on your servers. Multiply this across thousands of users making similar requests, and you've got a real performance problem on your hand. This is exactly the kind of inefficiency that GraphQL was designed to eliminate. Facebook introduced GraphQL in 2015 when it faced this exact challenge at a massive scale. Their mobile applications were struggling with the chatty, inefficient nature of REST APIs, especially on slower mobile networks where every byte mattered. Their solution was simple: allow clients to specify exactly what data they need. Nothing more, nothing less. GraphQL fundamentally reimagined how clients interact with servers. Instead of multiple specialized endpoints, GraphQL exposes a single intelligent endpoint. The magic happens in the query. The client sends a structured query that specifies precisely what data it wants, and the server responds with exactly that data structure. Instead of 3 separate API calls for the dashboard, you send one GraphQL query that might look like this. One single request, and you get back exactly what you asked for. No extra fields, no wasted bandwidth, no multiple round trips. The response matches your query structure perfectly, containing just the user's first name, last name, and the names of their last 2 ordered products. What makes this even more powerful is what happens behind the scenes. GraphQL uses a concept called resolvers, which are essentially functions that know how to fetch specific pieces of data. Each field in your query can be resolved by different services or databases. The user information might come from your user service, while the order data gets pulled from your order service and the product details from the catalog service. This architectural approach eliminates both overfetching and underfetching while dramatically simplifying how you compose data from multiple services. Your client code becomes cleaner and more maintainable because it's not juggling multiple API calls and trying to coordinate their responses. GraphQL shines in scenarios where you want the client or the calling service to have full control over the structure of the data. It also drastically reduces the number of requests made. This is particularly beneficial for mobile applications where network requests are expensive and users expect snappy performance. It's also powerful in microservice architectures where you have multiple services managing different aspects of your business logic, but need to prevent a unified data interface for your front-end applications. GraphQL can serve as that unifying layer, hiding the complexities of your backend architecture from your client applications. But GraphQL isn't a silver bullet, and there are scenarios where REST remains the better choice. If your use case is straightforward and well-structured, GraphQL might be overkill. It introduces additional complexity in your backend infrastructure, requiring you to set up resolvers, manage schemas, and handle query optimization. For simple applications with predictable data access patterns, REST simplicity often wins out. GraphQL can also create challenges when you need strict control over data access patterns. With REST, you know exactly which endpoints clients are hitting and what data they're accessing. GraphQL queries can be more unpredictable, potentially allowing clients to construct expensive queries that put unexpected load on your backend services. Security considerations also play a role. GraphQL's flexibility can make it harder to implement fine-grained access controls compared to REST endpoints, where you can easily restrict access to specific resources. If you're dealing with sensitive data and need rigid access control mechanisms, REST explicit endpoint model might serve you better. Now let's explore a communication pattern that takes a fundamentally different approach: remote procedural calls, or RPCs. While APIs make you think about endpoints and HTTP requests, RPCs ask a provocative question. What if calling a function on another server felt exactly like calling a function in your own code? RPCs have a fascinating history that predicates the modern web by decades. They emerged in the early 1980s when distributed computing was still at its infancy, long before REST APIs became the dominant pattern we know today. The core idea was elegantly simple yet revolutionary. Instead of dealing with the complexities of network protocols, HTTP requests, parsing responses, or managing endpoints, why not abstract all of that complexity away? With RPCs, you simply call a method, pass some arguments, and get the results back, just like normal programming. The magic happens under the hood, where your requests get transmitted over the network to another machine, processed there, and the response gets sent back seamlessly. To the developer, it feels like local programming, but the actual computation might be happening on servers thousands of miles away. RPCs regained momentum in 2015 when Google released gRPC, which has since become one of the most popular tools used for internal microservice communication. At its foundation, gRPC leverages HTTP2, which fundamentally changed how network communications work. Unlike HTTP 1.1, where each request requires its own connection, HTTP2 allows multiple requests and responses to flow simultaneously over a single connection. This multiplexing capability dramatically reduces network overhead and improves performance. However, gRPC's secret weapon is protocol buffers, also known as protobufs. Instead of using human-readable formats like JSON or XML, protobufs allow you to define your data structures using simple schema files with .proto extensions. You describe exactly what your service expects and returns, then compiles these definitions into optimized code for virtually any programming language: Python, Go, Java, C#, JavaScript, and many others. The auto-generated code handles all the complex work: serialization, which converts your structured data into compact binary format, transportation over the optimized HTTP2 connection, and deserialization on the receiving end, which reconstructs your data back to the native object. As a developer, you never get to see this complexity. You just call methods and get your results. This approach delivers remarkable performance improvements. Protobuf's binary format creates payloads that are significantly smaller and faster to process than JSON, leading to reduced bandwidth usage and lower latency across your entire system. gRPC particularly excels in microservice architectures where services need to communicate frequently and efficiently. When you control both the client and server side of the communication, you can generate optimized client libraries that make interservice calls feel like local programming. It shines when communication patterns are frequent and performance is critical. Think about scenarios like real-time price engines, authentication service for validating tokens, or recommendation systems that need to process thousands of requests per second. The binary efficiency of protobufs combined with HTTP2's multiplexing can deliver performance improvements that are immediately noticeable. gRPC also provides excellent schema enforcement through its proto definitions. These schemas serve as contract between services, ensuring that both sides agree on data structures, preventing runtime errors that can plague more flexible approaches like REST APIs. When you update a service interface, the compiler will catch compatibility issues before they reach production. The automatic client generation across multiple programming languages is another significant advantage. Your team can build services in Go, Python, and Java, and they can all communicate seamlessly using the same proto definitions. This polyglot capability is invaluable in organizations where different teams prefer different technologies. RPCs do come with some limitations. The most significant is tight coupling between services. Both clients and servers must understand the same interface definitions specified in the proto. When you update the service contract, you need to coordinate changes across all consuming services. This coupling can slow down development and deployment compared to the looser contracts of REST APIs. RPCs are also fundamentally synchronous, bringing the same dependency risk we discussed with APIs. When one service relies heavily on RPC calls to another, failures or slowdowns can cascade through your entire system just as they would with REST APIs. Perhaps most importantly, RPCs don't play well across organizational boundaries. While they're perfect for internal communication, external integrations become problematic. If a third-party partner wants to integrate with your service, they're unlikely to want to deal with protobuf schemas and gRPC clients. They'll expect familiar REST APIs with JSON payloads that they can test with simple HTTP tools. The key insight is that RPCs work best as private communication channels between services you control within your own infrastructure. Think of gRPC as a high-performance private line between trusted services, while REST APIs serve as your public-facing interface for external communication. In practice, many successful architectures use gRPC for internal service-to-service communication, where performance and type safety matter, while exposing REST APIs for external integrations and public interfaces. This hybrid approach leverages the strength of each pattern while avoiding their respective weaknesses. REST APIs, GraphQL, and gRPC share a fundamental characteristic. They all use a request-response pattern. The client makes a request and waits for a response. This synchronous nature works beautifully for many scenarios, but what happens when you need to move beyond the immediate request-response model? Sometimes you don't need an immediate answer. You might want to trigger an action and let it happen in the background. Other times, you want an event to cascade through multiple services without blocking or coupling them together. This is where we need to explore a completely different paradigm: asynchronous communication through message queues and message buses. Message queues fundamentally change how servers interact by introducing a fire and forget model. Instead of making a request and waiting for a response, the service sends a message to a queue and immediately moves on. The receiving service picks up that message when it's good and ready, processes it at its own pace, and everyone stays happy. Message queues aren't a new concept. They've been quietly powering robust systems for decades, evolving alongside our computing needs. Today, you'll find mature battle-tested solutions like RabbitMQ handling millions of messages for enterprise applications, Amazon SQS providing cloud-native queuing at a massive scale, and Apache Kafka processing real-time data streaming for companies like Netflix and Uber. What makes these systems so powerful is their ability to keep your architecture resilient and scalable, even when individual services are struggling or traffic suddenly spikes. The fundamental concept is simple. You have a producer, which is any service that needs to send a message. This message could be a task that needs completion, an event announcing something important, or data that requires processing. The producer pushes this message into a queue which acts as a reliable holding area. On the other side, you have a consumer, which is any service that listens to the queue and processes the message as they arrive. The magic happens in the middle. The queue acts as a buffer, decoupling the producer from the consumer so they can operate independently. Let me illustrate this with a scenario. When a customer completes an order, you want to send them a confirmation email. With REST APIs, your order service directly calls your email service and waits for a confirmation. If the email service is slow or down, your entire checkout process fails. With a message queue like RabbitMQ, the story changes completely. Your order service pushes an order confirmation message to a queue and immediately shows the customer their successful order screen. Meanwhile, your email service processes the message from the queue at its own pace. Whether the email sends instantly or takes a few minutes, the customer checkout process remains smooth. This is the fundamental beauty of the asynchronous design. It allows each component of your system to excel at what it does best without being held back by the performance characteristics of other components. Message queues are perfect for background processing tasks that don't need to be completed immediately. They also excel when you have mismatched processing speeds. If one service can produce messages faster than another can consume them, a queue acts as a shock absorber, allowing the fast service to keep working while the slower consumer catches up at its own pace. They also create loose coupling between services. Instead of service A directly calling service B, both services only need to know about the queue. This makes the system much more maintainable and allows you to update or replace services without breaking the entire chain. However, message queues aren't appropriate for every situation. The most obvious limitations is when you need real-time responses. The asynchronous nature of queues introduces unacceptable delays. Message queues represent a powerful paradigm shift from the immediate synchronous world of APIs to a more resilient, scalable approach where services can operate independently. They're particularly valuable in complex systems where you need to coordinate multiple operations without creating brittle dependencies. But what happens when you need to go beyond that simple point-to-point messaging? What if one event needs to notify multiple services simultaneously, or you want to create complex workflows where different services react to the same trigger in different ways? This is where we explore an even more sophisticated pattern: message buses, which take the concept of asynchronous communication and expand it into a rich event-driven ecosystem. Think about how breaking news spreads in a modern media landscape. When a major event occurs, the original source doesn't call each news outlet individually to share the story. Instead, the news breaks on a wire service or press release, and within seconds, it propagates everywhere. Traditional TV stations, radio stations, online publications, social media platforms, news app, and even your smart speaker. Every channel receives the same information simultaneously, then handles it according to its own style and audience. This is precisely how a message bus operates in software architecture. It's like having a town crier in a digital square announcing important events to anyone who cares. A message bus fundamentally changes the communication pattern from one-to-one to one-to-many. When one service publishes an event, multiple other services can subscribe to that event and react independently. Unlike message queues, which typically connect specific producers to specific consumers, a message bus is designed for broadcast-style communication that can reach any part of your system that's interested. The technology has matured dramatically over the past decade. Modern message buses like Apache Kafka can handle millions of events per second across distributed clusters. Google PubSub provides cloud-native event streaming with global reach. AWS EventBridge connects hundreds of different services and applications. NATS delivers ultra-low latency messaging for real-time systems. Redis Streams combines the familiar Redis ecosystem with persistent event streaming capabilities. These platforms have evolved into lightweight, distributed, and remarkably fault-tolerant systems that can power everything from small startups to global enterprises, processing billions of events daily. Here's how they work. A producer, also called a publisher, emits an event to the message bus. This event represents something significant that has happened in your system. A user registered, an order was placed, a payment failed, inventory levels changed, or any other business events worth announcing. Multiple subscribers can listen to the bus and react to these events in completely different ways, each handling their own piece of the puzzle without knowing or caring what other services are doing. Imagine a monthly subscription payment fails in your system. In a traditional API-based approach, your payment service would need to individually notify every system affected, creating a web of complex dependencies and potential failure points. With a payment bus, the payment service simply publishes a payment failed event and moves on. Your notification service immediately picks up this event and sends an email or a push notification to the customer, letting them know that their payment didn't go through. Your billing service sees the same event and automatically flags the invoice as unpaid, while logging the failure for accounting purposes. Your account status service might pick up the event and mark the account as pending payment. Meanwhile, your analytics service captures this event for business intelligence dashboard, helping you track payment failure rates and identifying patterns. All of these interactions happen simultaneously and independently. Message buses excel in scenarios where you want to embrace an event-driven architecture. This architectural pattern treats your entire system as a collection of services that react to business events rather than calling each other. It creates a more resilient, maintainable system that can evolve independently. They're perfect for when multiple servers need to react to the same event. Instead of the originating service needing to be aware of every downstream dependency, it simply announces what has happened and let the interested parties respond appropriately. Message buses also shine when you anticipate growth and changes. Adding new subscribers to an existing event is a trivial process. For real-time insights and monitoring, message buses are invaluable. You can have dedicated services listening to various events, feeding real-time dashboards, triggering alerts when anomalies occur, or powering machine learning models that detect patterns across your business operations. With that said, the most significant limitation is that, like message queues, message buses are not fundamentally designed for the request-response flow where immediate confirmation is required. Message buses don't provide the built-in handshake mechanism that synchronous communication offers. There is no guarantee that any subscriber will process your event, let alone respond to it within a reasonable time frame. For time-sensitive and critical operations, you still need the reliability and immediate feedback of synchronous APIs. Interservice communication forms the foundation for modern software systems, and selecting the right approach is key to building resilient and efficient applications. We often start with RESTful APIs, which is ideal for straightforward synchronous communication, but can become inefficient when many dependent calls are chained together. GraphQL comes into play when our system has scaled significantly and we want the flexibility of services requesting exactly what they need. When performance and speed are critical, especially in microservices that depend on one another, RPCs step in to offer direct procedure calls. Although fast, their tight coupling can introduce challenges in complex distributed systems where robustness, fault tolerance, and recoverability are crucial. To address the need for decoupling, message queues enable asynchronous communication, making them perfect for situations where immediate responses aren't necessary. We then have message buses that facilitate event-driven setups by broadcasting events across multiple services, allowing systems to react and adapt in near real time. That's it for this one. If you're new here, my name is Uma. I am a software engineer and content creator. I enjoy learning and breaking down complex technical topics to make them easy to understand. I also coach software engineers through technical interviews and other career areas to help them learn and increase their earning potential. If you found this video helpful, don't forget to give it a thumbs up and subscribe for more deep dives like this. If you'd like to be coached by me, click the link below or go to umacodes.com. Also, check out Beyond the Build podcast hosted by me and my good friend, where we talk about everything related to software engineering that isn't technical. Thanks for watching, and I'll catch you in the next one. Peace.